Guys, so this is a video for the Ergun equation and pressure drop in a packed bed reactor, and this applies when you're using gases. And why not liquids, right? Why wouldn't you want to consider pressure drop with liquids? So here's the reason. Well, so I have a packed bed like this, and I got all these little dots. That's your packing, right? I'm kind of going kind of fast here, but so when the fluid of a liquid flows through, right, the density of that liquid throughout the whole column, right? So the density over in this little plug compared to this little plug, it's going to be the same for liquids because it's incompressible. And why would you want to consider pressure drop? Well, pressure drop, or pressure in general, for a liquid will not change the concentration. It will not change the density of that liquid. And when you're dealing with your RA is equal to, I don't know, a first order, this is not going to be affected. And this is only due to temperature, so you don't have to worry about that. So this is due to density, and pressure affects density of gases and doesn't affect density of liquids. Okay? So that's why we only care about this equation, or considering pressure drop, when you're dealing with gases through a packed bed reactor. Okay, so that's just a quick demonstration. I just want to make that clear. So it's always good to know, because you got to know when you're going to use each equation. So we do not consider pressure drop in a packed bed reactor when it comes to liquids. Now second, we're going to take the same thing I've done in other videos, the material balance of a plug, and we're going to come up with equations real quick when dealing with gases in the packed bed reactor. So let's take that plug out here like we usually do, right? You'd have your flow rate in, flow rate out, initial flow rate, final flow rate, and then your generation term within the plug. And remember, this is a DW plug. It's all in other videos. And we're going to do the material balance. So in minus out plus gen equals accumulation plus. Sorry, drank a lot of coffee. My hand's a little shaky. So this steady state, everything else stays. So in is FAO. You're out. This is the incremental step theorem. Again, other videos. I'm trying to make sure I make it through at least the first part of the derivation of equations. And this method will work when you have first order, second order, or third order reactions. Like this. Okay, so other videos explain, sorry, that should be FAO. Like this. Other videos explain what I'm doing here. For the sake of time, we must move. Sorry, that's prime. Prime because we're dealing with weights, not volumes. Go 0. Okay, so now we want to take care of the DFA. So FA is equal to FAO 1 minus X, right? So take the derivative. So the first thing I'll do is I'll distribute the FAO into the 1 minus X. Alright, now I'm going to take the derivative in terms of X, which gives you negative FAO. And then our DFA is negative FAO dx. Now we're going to sub DFA into that material balance for this term in particular. Okay, so let me move that Ergun equation down. We'll be using that here shortly. So negative DFA, plug in this guy in for it. You're going to get FAO, the negative signs will balance, dx dw plus RA prime equal to 0. Okay, so now let's isolate dx dw, right? Is going to be equal to negative RA prime over FAO. Now we got to make an assumption. So this part of the problem is when you're going to deal with the order of reaction. I'm going to go with first order just to make the theory a little easier. It'll change your integration and all that stuff later on if you put second or third order in. But just for the sake of the video, I'm going to assume it's first order. Okay, so now you have dx dw equal negative RA, which is KCA FAO. Now here's the thing. You're dealing with gases, right? So this equation is called, it has to do with the expansion factor, and it's something I went over in another video. And it comes out to be CAO, right? 1 minus X over 1 plus expansion factor e to the X. P over P naught. T naught over T. Okay? So I'm going to leave everything in like that. So I'm going to plug CA simply into here. dx dw is going to equal to K times CA naught. If you use this enough, you're going to realize, hey, I'm memorizing this equation. It's ridiculous. It's quite a sizable equation. The derivation is not too easy, but it's kind of impressive how you just, remember these equations after you use them enough. And you'll use this one a lot. This one. You'll use that a lot. Okay, so now we got a dx dw. And this is where the thought comes into pressure drops, right? So you're thinking, oh, well, this accounts for pressure drop. Well, it doesn't. Not yet. You got to do something else. Because right now, what we got is we got our x as a function, I'm not going to say equal to, something like that, is a function of pressure for one, right? And conversion. Right? Or, what was it saying? Yes. Yeah, I was going the right direction. Pressure and conversion. I just want to make sure I got that right. Yeah. So yeah, it's a pressure and conversion. So to solve something like dx dw, right, as a function of pressure and conversion, we need something else. We need another equation, another differential equation. And what we're going to need is dp dw, basically. So that we have this in terms of w and we can solve it. Okay? That's a differential thing. So if you want to solve this, we got to work the Ergun equation down. We got to make sure we get dp dw. So how do we do that? And I'll show you. You can use MATLAB after this to solve this. So in the next video, so I don't run out of time, I'm going to explain how you get down to dp dw. And what you're going to see is we're not going to write dp dw. We're going to write dy dw. Because y is going to be equal to p over p naught. Spoiler alert. This is a very hard derivation, but for now, for this video, all I want you to remember is how we got this equation in daring red. Look at that. I love this red color. But how we got to this equation, that's what this video is all about. And we need, and to understand that we're going to need another equation, for dp dw. And what we're going to end up to solve this for conversion volume and get equations that we need is we're going to need to solve two differential equations, dp dw and dx dw. And in this video, we got dx dw. Okay, so this is going to be quite a long series of videos, but this is how you do with pressure. And as I said, or maybe I didn't say, but this is the pivotal point of this class. This is the hardest part, is dealing with the Ergun equation, pressure drop. I found this to be the hardest. So in the next video, we'll get dp dw. All right, see you next video.